Good afternoon and welcome to the 2:30 session. Very happy to be presenting here today. I'm Dr. David Corliss from DTE. I'm a senior data scientist. We are the people who send you your power and keep the power on. It's more in the second category that we'll be talking about today. The particular area that I work at in DTE is in emergency response. For example, when we had the storm, how convenient that we had that really awful storm the afternoon before this presentation. We were watching that storm days in advance to figure out how many people, to estimate how many people would lose power, where and when, the timing of the storm, these kinds of factors, so we could have the fastest possible response, so when people sadly do lose their power, we can get it back on as soon as possible. This talk is about the AI that we're using to make that happen. So first we're going to give a broad overview of the project. We're going to look at the data sources. In this case, we're inputting weather data. We'll talk a little bit more broadly about other things we can get from, this is government data sources, and how we determine feature importance. There's a lot of different things we can look at. And so feature importance was one of the most challenging parts of this particular project, identifying the things that really matter. Analytic methods, talk about the multiple different methods that we are using in this particular model. How do we measure the performance? How do we know if it's really working? And then have some time for Q&A. So first, let's give an overview. What we want to do is deliver a product. So this means that we're talking about a business solution. Yes, it's a scientific talk and a scientific application, but as I had a chance to comment earlier in another session, one or two might have said, any scientific difference smaller than a business decision does not exist. In the end, this is science in the service of a business solution, ultimately, and this is going to come more in at the end of the talk, ultimately in service of the public, because we are a publicly regulated utility, it's a private company regulated by the Michigan Public Service Commission. And so we want to make sure that we're delivering the most value and while at the same time delivering the fastest response. So give a general idea of what we're looking at. First of all, we're going to use publicly available data. Now, it turns out there's a lot of work involved in leveraging that. We'll talk some about that. But we're going to use publicly available data. I pull back a little bit in calling this data free. The fact is this data is paid with your tax dollars. So if you want to look at your personal, no, this is an important point I want to make in this talk. We're using, quote, free government data. Well, actually, it's something that's paid for with tax dollars, and so if you look at your tax statement, personal or corporate, you're going to see that turns out you already paid for this. So it wasn't free, you already paid for it, so we're here to make sure you get your money's worth. The data used to drive this project is like a national park or a post office. It's owned by the entire American people. We've already paid for it, and we want you to get your money's worth. And it turns out that weather data is just one kind of data that the government will give free to the end user at the point of use. We're going to have an example here of using weather data from the National Oceanic Atmospheric Association Administration, curiously pronounced NOAA. But that's the name of the organization. We're going to be look at how we use their data. And then we're going to match that to history data of all the outages that have happened in the past. Well, not forever in the past, but we used a 5-year time period. That's a really useful time period to look at. There's a reason why we didn't want to go shorter or longer. If we had just 1 year or a few months or something like that, well, it turns out that the kinds of weather we have and the kind of problems we run into are different at different times of the year. So it needs to be evenly balanced throughout the year. Seasonality and seasonal changes are one of the important things that we're detecting in the model, and seasonal changes become a feature in the model. So in that case, it's just the seasonal pattern of outages going up and down at different amounts at different times of year. And so we're not just having the outage data as an outcome, but we're also mining that for any patterns that we're going to see in it. Then we apply analytic modeling methods, multiple modeling methods. You're going to see a little bit of detail about a group of regression models today, but we've actually used a number of variety of methods, and we're ensembling them. We're using a means to combine the result from multiple methods to predict a single outcome. This is very much something like something you've already seen if you've seen, for example, weather forecasting when there have been very severe storms, for example, hurricanes. That might be out in the Atlantic Ocean, say, and approaching the American mainland, and you see multiple tracks of the hurricane. Each one of those is a statistical model. In the same way, we're looking at severe storms that are coming in to the Detroit metropolitan area and up into the thumb, the Detroit, the DTE service area, and in southeast Michigan and eastern Michigan in the thumb. And we're looking at multiple models that make multiple predictions and ensembling them, combining the results of multiple models to get a better result. So it isn't just one modeling method. So we start with the NOAA data, which is free per use. It takes a lot of work to get it to actually work for us. Match that to outage history. Put that through a series of analytic routines, and the result is we're able to predict how many outages on a given day, a little bit in terms of timing, and it allows for faster response to a storm. Here's a business description. Remember, we're talking about a product that is intended to deliver business value. So here's the idea behind it. There's actually 3 different groups of people. There's a data science team, but it turns out the predictions we use aren't actually sent directly to a business customer per se. They're actually one of multiple inputs to a meteorology team. So guess what? We're a utility company. We have electrical utility. We have a meteorology team. Big surprise. We have our own group of people that are specialized in our own particular area. What we're seeing in this project, which started in November, so it hasn't been around that long, is trying to use advanced modeling techniques, in particular, physics-informed AI. We'll get into that in a minute. The data science team is using advanced modeling methods, and we hand the results of that model to a meteorology team, and they make a forecast. So it's a combination of 3 critically important stakeholders. There's a business team that needs to know how many people to deploy at what time. There's a meteorology team that wants to have an accurate forecast, and there's a data science team that's helping them make a more accurate forecast. So what we're starting with is they're already making this prediction. This would be similar to, a loan company has been predicting risk as long as there have been loan companies going back to the 1500s. But now we're using AI to make a better prediction, and then that serves the interests of the business team and the business results. So all 3 stakeholders have to participate equally. If we were just, we are not a university math department. If we were just making a line on a graph that didn't drive value, there wouldn't be any value and they wouldn't be funding the project. So it really is science in the service of business results, and 2 science teams, not one of the meteorologists, the other the data scientists. My own background, I have a PhD in statistical astrophysics, have done a lot of study in longitudinal statistical analysis, how large groups of things change over time. It's a good adaptation to good application of this particular usage. The weather team has started calling me the resident physicist. It's a good description, but that's just one person on a much larger team, and it's this partnership that really makes it all work. So let's talk about data sources. Now, it turns out to build the model and to use the model, those are 2 different things. Now, one of the things you will find, let me ask you, has anyone ever used data from a government website? Maybe it's unemployment data, economic data. Most folks, not everybody. Usually, it's a very unpleasant experience. The data are, I see people laughing, shaking their heads. The data is an absolute mess in an unusable form. One of the biggest challenges is simply getting the data from the form that it gets collected into a form that can be used for business. There is an entire industry. There are a series of companies that exist for no purpose other than taking the horrible data format, this is not a complaint, horrible data formats used by the government and turning them to a useful format. Some folks, however, do this for free, and at this point it really is for free, unless you live in the state of Iowa. Turns out that Iowa State University, which has a wonderful statistics team as well as a great meteorological team, the agricultural college, weather affects the farmers there, agricultural college at the Iowa State University has taken the very, very difficult to use NCEI NAM data, that's the name that NOAA calls it, and put it in a very useful form, very easy to use, very easy to adapt. You can see the list of fields over there on the left-hand side. It's not everything that's available from the government, but it is enough to get a very good start, and they put it in a very useful format. So you can simply go out to their site. They have a very nice API. It's a web browser. You can pull data from a particular day. They have archived weather forecasts. So this isn't today's current weather. You'd have to get that from somewhere else. You'd have to get that, what's the current forecast? You don't get from there. This is an archive, but it turns out that, no surprise, the folks who produce the weather forecast for today and tomorrow and the next day, that team has not archived it going back 5 years, and you need you need multiple years, because not all years are the same. Last year was a very bad year for weather in terms of electricity in Southeast Michigan. And so you wouldn't want to build a model just on last year. You'd be over-predicting it all but the very worst years. So 5 years is pretty good. With climate change, the numbers aren't exactly stable. The numbers keep going up. So 5 years is a really good number to go back in time. The government doesn't have an archive. They don't have yesterday's data. They've got tomorrow and the next day and the next day. But Iowa State has archived it so that people can do planning for farms. We're using it to plan for summer thunderstorms and ice storms in winter, things such as this. So they have a fairly easy to use API. You can download the data over an extended period of time. We got 5 years worth. I would call this a short list, because if you look at the actual source data, there's about 500 different things the government actually captures in terms of weather that are available. But if you look at this site, it's a very easy to use format. Just as an example, for people who might have used government financial data, the Bureau of Labor Statistics creates the unemployment data. Don't go to them for the unemployment data. Don't get me wrong, they're the source, but you go to the St. Louis Fed, and if it's economic data in the US, go to the St. Louis Fed. What Iowa State's done for weather, St. Louis Fed has done for all the US. You want to track gas prices going back 20 years and how has it changed over time. Go to the St. Louis Fed. Just as an example of another organization that's taken the raw government data and put it in a usable format. So we all own the data. We've all paid for the data. It's like a city park. Any of us can go there. But finding it in a format that you can actually use can take some searching. In this case, for weather data, of course, this is anything you want to do. You want to run a lawn service. You want to, you're running a stormwater treatment center. You're doing anything that's impacted by the weather. There's a lot of things impacted by the weather. You can go to this site at Iowa State, get years of history, and be able to predict the impact from a current weather forecast will have in the near future. So, what makes it physics informed? Well, it isn't just reading in a bunch of data and making a prediction. When the rules of science, when the rules of physics become constraints in the loss equation, sorry if I'm talking technical data science for just a moment, when physics limits what the outcome is going to be and makes it more accurate, that's where we're getting into physics-informed AI, the so-called loss equation. Often expresses the thing you're trying to measure or how accurate that thing is. When we're working in AI, it's a critical understanding of, it basically ends up driving your final result. When physics becomes restrictions, mathematicians would say constraints, in a set of linear equations, for those who were here for the last session, in the hard math that actually governs what the answer turned out to be. Then we get into the realm of physics-informed AI, where the laws of physics become a contribution to, temperature can't can only go up and down so fast, for example. When you've got high wind speeds in one area, they tend to move into high wind speeds in another. Changes in air pressure drive changes in wind speed. The reason why the air moves around is because changes in pressure. And when these laws are figured into the science that gives you the outcome, you start getting into the area of physics-informed AI. So that's what we're doing here. So being the resident physicist on a team is actually a very nice, very good spot to be in. But again, it takes people who are weather experts. I say at least once a week. I am not saying, I'll say something that sounds like a weather statement. I am not a meteorologist. I'm a statistician, but I do read weather data. And so it's this close partnership between the meteorological scientists, data scientists, physical scientists, and the business that use the results. The three-way partnership is what makes this successful. You see a lot of, I worked for years and years and years in the automotive industry. Chris Smith, who spoke earlier, talked about that kind of environment. Is another situation where that close partnership between multiple stakeholders is really needed to make the a successful project. So here is our area. It turns out that there are some places in Southeast Michigan with more people in them than others. And because of that, there are more electrical lines. So the same storm that comes through like we had last night is going to knock down more lines in Detroit than it does in Bad Axe, because there's a whole lot more people and lines in Detroit. And they have different weather. And the lakes, you really can see it in the data, you know, between west to east and things like that. And of course, it's a big piece of real estate, so the weather won't be the same in all places. And so what we end up doing is not having one model. The features are different enough from size, from things that matter, from things that are close to the lake or more inland. It's so different that each one of our 12 major service centers, which are shown on the map, gets its own separate model. It's the same kind of model. We're using least squares regression. We're using decision trees. We're using neural nets. Neural nets tend to be black box. But at the same time, that's not as much a risk in this particular case. Just the same, the one that's being put into production was a combination of decision tree and neural net. We use random forest. We use a number of different methods to ensemble them. But each individual geographic area where DTE has a service center with trucks and repair crews and that kind of thing that they have to send people out of to fix the damage from the storm, each service center and its area gets its own distinct model. Similar architecture, same source data, but different outcomes and just different things happening with the weather. You know, something, for example, a good example of physics-informed AI. This time of year, trees are starting to leaf out. The amount of wind it takes to break a tree limb is lower when there's leaves on the trees. When the trees are full of leaves, they get knocked down by 25, 35 mile an hour winds. In the winter where there aren't any leaves, they get knocked down by 45 mile an hour winds. Just as an example of how you can take wind loads and use that as an equation that informs the final result. This is a physics informed part. Well, there are places that don't have a whole lot of trees because they're full of sugar beet fields. There are places that don't have a whole lot of trees because they're full of skyscrapers. So you get different kinds of area. They're going to have different kinds of things going on that affect their particular weather. And so each individual, about a county size, or maybe a couple counties, roughly county-sized pieces of real estate here, each one is going to have its own statistical model with its own prediction. And to get the total for the whole area, we just add them up. But each individual large chunk of real estate gets its own individual model. And then to get a total, we sum them. Decision trees. Decision trees we found are good for two things, actually. Decision trees are perfectly legitimate modeling method. They're good for classification. You can interpolate the numbers at the bottom of the tree. Okay, well, you landed in this bin. You're not in that bin, but you're closer to the middle of this bin, but you're a little to the right. Okay, well, we're going to interpolate that and get a final number, not just a bin, but a final number. This is called a regression tree. So we used a regression tree method as one of the methods. And so it's just another machine learning method like random forest and all the rest. But at the same time, decision trees are also really good for feature identification, for finding the things that matter the most, because they end up at the top of the tree. So one of the things we did to screen the 40 variables that went in to the maybe 6, 8, 10 that went into the model for each individual location, each service center, 8, 10, 12 variables tended to make the final cut. One of the things we used to find out which ones were the most useful was decision trees and looking at variables that consistently came up to the top of the tree. We also used a random forest to predict feature importance. And then once we had this shorter list, we skinnied down the list. So we started with this really, really long list. Well, I don't think it's long. I've mined World Bank data with 2,400 fields. The poor guys who do genetic analysis, same methods, do genetics, like which gene is broken here? Well, beats the heck out of me. There's only 40,000 of them. But at least for us, having 40 is a fair number of things to measure. So what we'll do is start with a very, very long list. We'll skinny it down to 40 or 50 or 60 that we can use to start building models, then skinny them down to the last dozen or so often that are actually making a difference in the result. Now, in this particular case, not only do we have 12 models, but we actually have 24 because we have separate predictions for 72 hours in advance, 3 days, and 12 hours in advance. One of the things that DTE will do is they'll classify storms by how bad they are. It's a little bit like a credit score. It's a lot like a credit score. We use a lot of the same methods. You know how you get an exact number? Oh, your credit score is 713, and that's better than 14. Better than 12 and not as good as 14. Well, it's not a whole lot of difference. It gets put in the same bucket. We take the number of outages and we put them in buckets. We use a classification 3 days in advance to get an idea, well, is it going to be a regular day, a little more, is it going to start being a bad day, or levels of storm. We do a classification system 3 days in advance. And we also do an exact prediction, as in a specific number for each location 2 days in advance. And we use it for planning. If we tried to do this the day of a major event like yesterday, then it would be too late to plan. So one of the business rules, I talk about this three-way partnership. It isn't just data science, it isn't just physics, it isn't just the meteorology team. It's the business team telling us that if we don't know 2 days in advance, forget about it. Because we can't call people into work and change schedules and allocate resources to the different service centers inside of a 48-hour window. We need a good prediction 48 hours in advance. We need a ballpark classification 72 hours in advance. Those are business requirements in the system, and they can't move. That's part of that three-way partnership. So we're doing a 72-hour classification model. What level? Like a credit score. Binned in, good, okay, poor, really, really high, excellent credit. That's the 72-hour, 3 days in advance. And then 2 days in advance, we're saying this many in each service center, give or take some. We give the uncertainty to the business as well. So how are we doing this? Lots of different methods. These are all the different ones that we've tried. We find that some work better than others. I have to say, XG Boost, for example, it was a lot of Kaggle competitions and was definitely on our must-look-at list. But for this one particular application, it performed poorly. I am not saying don't use XG Boost. I'm saying the opposite. I'm saying look at it every time, but look at multiple methods and test them. Don't just run the code and then pack the numbers in. You have to test each individual method to see which one's working well. There was a surprise when we developed it. Turned out that XG Boost performed badly. This is the first time I've seen it come in last in the horse race, as it were. But we have a number of different methods. One of the things that we are very sensitive to, linear regression is a very, very common tried and true method, and it's the one the company decided to put in production. We're running the other models, we're looking at them, we're monitoring their performance, but to put it in production and make a bet on it, and I'm talking about bets every day of a couple $100,000 if we're wrong about a storm. It's a lot of money on the line. then they're making the bets on the regression model, and the others are sort of taken into advisement. That's going to continue to advance as we go forward. It's a fairly new system. We use classification methods. Remember, now we're talking about 3 days in advance. What level does it come in at? So we're looking at a lot of different methods. We throw out the ones that just aren't performing as well, and then we'll ensemble. Sometimes it's averaging. Sometimes, oh, for this particular occasion, we think this model is better. We find that some of the models do especially well for really bad days, and other models will do especially well when the weather's not so bad. But it isn't just the day; it can be by location too. So, for example, yesterday's storm was really not a big deal on the northern end of the thumb. Pretty bad around here. It could be worse, but it wasn't as bad. That's one of the things we're able to predict. So, with multiple models, we had one model predicting north of I-69 and another set of models predicting south, because we found that for a given event, the more intense it was pointed us in a direction of one model, and in an area where it wasn't so bad, it pointed us at a different model. Having multiple models and averaging them, or voting, this model said this category, that model said that category, normal got 5 votes, and really, really bad got 2 votes. We think it's going to be normal, but it might be on the high side. Something like that. So these are the different methods we tried and ensemble. Here's a map of our service area broken up into the 12 regions. Now, we talked about how each of the different service centers are different enough that they need their own model. But there's another advantage as well. So it isn't just localization because they're different and because different numbers of people live there and different numbers of houses going to wires, that sort of thing. But also, what we find is that, we'll call this, the technical term for this is boosting. There's a little bit of uncertainty. There's some plus and minus. There's a range. It happens for every one of the 12 models, one for each one of these 12 geographic areas. But when you add them all up, the random pluses and minuses, they tend to cancel each other out, and it gives a more accurate forecast. If we did one forecast for the whole area, we wouldn't get the benefit from boosting, where the pluses on the average, just a little bit of noise, this one coincidentally a little high, that one coincidentally a little low. When you add 12 of them together, it shrinks down the noise by the square root of n, at least the theorists say, and it makes for a more accurate forecast overall. So this is one thing that by having localization, not only did it have more focused on each area, but it also tended to shrink the overall amount of noise. Here's an example of a random forest. It's one of the methods we looked at. When we look at the performance of the model, in this case, our prediction from the model, these are daily totals for the Ann Arbor Service Center in 2021. So this is a year's worth of stuff. And you look at the blue, that's the actual number. You look at the orange is the predicted number. You can see how it follows along. You can also see, what I found, anybody else find this? Let me ask this general audience. Data science, we really like something called the confusion matrix. Number of times it gave yes and it was, yes and it wasn't, no and it was, no and it wasn't. Those 4 things make up something called a confusion matrix. What I find is that something like this and talking through it makes a whole lot more impact with the business. They seem to understand this better than the simple 4 numbers of the confusion matrix. In this case, I can talk about this and say, well, generally it works. You notice, though, the predicted runs a little high in some seasons. The baseline seems a little bit high in a number of places. We find that there's very, very quick responses to some storms, but the storms tend to be of longer duration. This particular model is indicated by, it tends to work best on the first day of a bad storm, but not as good on successive days of multiple storms. I can put up a graph like this and explain that to the customer. And they seem to understand that better than if I just put a confusion matrix, false positive, false negative, true negative. We found that just explaining this, and this is the random forest from Tim Leonard, absolutely brilliant data scientist on the team. But showing the graph of predicted versus actual and walking people through the results really helped them understand it. Sequential models. Weather tends to run in patterns, as I'm sure we've all noticed. If we want to know the weather tomorrow, the best thing to do is look at the weather today, because it will probably carry over for the day. Because, generally speaking, we had a fairly significant thunderstorm last Friday. We had one again yesterday. So we're in a kind of a turbulent period in the atmosphere in this part of the country. That's going to calm down in a few days, at least that's what the forecasters say. But weather tends to run streaky. A few days of one, a few days of another, it goes back and forth. We're looking more, I literally wrote my dissertation on how to do this. So this is a reason for being on the team. When we find patterns, what we can do is look at other points in the past when there have been similar patterns. What you're looking at up here is financial data, not weather data, but it illustrates something called similarity analysis. This looks at recession and boom and bust cycles in the US economy. And what we can find is that some recessions look like earlier recessions, and we expect them to follow along the same pattern. So this is a mathematical method. We can look at a stormy period and say, oh, this, at least starting out, looks very, very much like a similar storm period we had 3 years ago. How did that play out? So some of the science we're putting in is a little bit like classification, is finding past points in history where for several days we had a very, very similar looking storm, and then we would look at really rare events like, okay, the storms that were most similar, did they have any tornadoes, or did they have really, really bad lightning or something like that? We could look at yesterday's event, which certainly put down a lot of rain. How many folks were out in that rain or saw it? It was a huge downpour. Not a lot of lightning. A lot of rain, not a lot of lightning. That was a characteristic of that particular line of thunderstorms. We could find other thunderstorms in the past that looked like that and make that identification in advance using the sequence. Not just at this point in time, this is what the regression models do. At this point in time with this much temperature, and here's the dew point, and here's the wind speed, and at this instant, we expect to see how many power outages in the next day. In this case, we're looking at multiple days in a row, and we're putting them into bins and looking at other events in the same bin and using that to improve our prediction. So these are sequential models. Tim Leonard, my partner in this business, is especially good at these sequential models, and we find that they're very useful as well for weather, because weather runs in streaky patterns. So here's our an example of our neural net model, predicted versus actual. This, go for it. We thought we'd already seen that. So how well does it work, and how do we tell the business how well it works? Well, here's the actual performance of this model. This is from this year. This is from early this year. So we've been up and running this model since the end of December. And you can see that in this case, once again, we've got the actual number is a blue dot, the predicted is an orange dot. We have a little bit of a range and uncertainty around each one. And so what we're interested in is how many times the dots are outside of the range. And now when we can deliver, you look at the bottom, what are the numbers? If you want to predict the class, how severe the storm was. 72 hours in advance, 94% of the time we got the right level, like a credit level bucket. And at 48 hours, we were at 100%. That's a really good number. It means that we can deploy people appropriately. We're getting a good early warning system. We want to get the number within 50 of the actual. On a quiet day like today, we'll get about 150 power outages in the Detroit, in the DTE service area. About 150 outages on just an ordinary quiet day, like today. Are we within 50? We were within 50, 53% of the time. On 3 days in advance, 2 days in advance, that's up to 75%. We can do better. And so CI/CD, the models continue to develop and continue to improve. So there's nothing that can't be improved. Old Henry Ford said that. And so we continue to improve these models. But this is acceptable performance, and the models were put into production. Changing gears a little bit. Responsible AI. We've talked a lot about this. This is what a responsible AI looks like at DTE Energy. A couple of guiding principles. Transparency, publicly available data. Anybody can download these data. Maybe a bit of work to make it look good or make it usable, but there's no secret data. There's no internal company information. Even the outages, they're available on a website called DTE Outage Map. If you want to look at it, how many outages, some of you, I see people nodding their heads. So the outcome is something that's publicly available. The input weather data is something that's publicly available. So there's transparency and the ownership of the data. People call in these information. They tell the company, so it's the company's money, but it's in partnership with people who are sending us the information. They call in a power outage. And so notice as we go to point B, customer provided outage information. The customer provided this information to us. We have a commitment to keep it private. We can tell people, oh, there's 3 people out in your neighborhood, and I'm sorry, but there's 3,000 people out on the other side of the mile road, and we're going to have to do that first because it's a big thing. That's where the crews are, and you might have to wait a little while before you get just the tree down in your backyard that only took out power to your house. We're very sorry, but we have to get the 3,000 people across the road first. But we can share that information, but we're not going to share what houses are out. You go down to a certain size, it begins to disappear. You don't know what individual houses are out. There's a limit to how much you can zoom in. We have a commitment to privacy and to ethical use. People give us this information so we know that there's power out and we go out and fix it. And then we use this in our ethical AI to improve service to those and other customers. This gives us faster response. We have an ethical commitment to the customer to use their data in a secure manner, in a trustworthy manner. We're not going to do bad things with it or monitor them otherwise or something like that. And we're going to use it in their service to improve their service. Bias mitigation. Every field is tested for bias. Now, we're really lucky here because this is weather data, but if we had other kinds of data, we'd be more concerned. If you're trying to do the same kind of thing to determine who to hire and who not to hire by reading resumes, there's a lot of data science around that. It's a very, very similar thing. Who are the kind, you want to know what the weather is going to be like and how many outages we're going to have at the end of the week? It's very, very similar to reading a resume and trying to project what the job performance will be 2 years out. Same kind of science. But in this case, there isn't any inherent bias in the data. What's that old saying that God sends the rain on the just and the unjust? It doesn't matter who you are or what kind of person you are, you're going to get the same weather as your neighbor. Maybe your tree that falls is not your neighbor, but you'll get the same weather. So using weather data, we have that little bit of a protection there, but even so, we're still testing the individual predictors to see if there's any risk of bias. We have deliberately chosen not to put in personal information or other kinds of information that might help identify a specific individual for someone using the outcome of that model. So we're protected against having favoritism towards one group or area or anything else as a result of the numbers that come out of the model. And that gives us to our last statement, a commitment to public service. Yes, we're using advanced AI, but why are we doing this in the first place? We're doing this to make the electrical grid stronger, better for everyone. When power goes out, we can restore it faster because we know better how to deploy our resources. In conclusion, we're doing a 72-hour classification, 48-hour count. We use multiple modeling methods. We use them all on each one of 12 separate service centers areas. CI/CD, nothing exists that cannot be improved. The models continue to get tweaked and improved as we go along. Questions? How long did I leave you? Are we out of time for questions? We have 5 minutes. Thank you. Contact information.
Oh, okay. Wasn't expecting a mic, but okay. So I was just curious, with your work with the meteorology team, do you find any variability depending on the weather event that occurs, like whether it's a wind event or a precipitation event with your work?
Yes, very, very much. And so, for example, in the last week, to cut to the chase, last week we had some bad weather. That was mostly wind. Last night we had a line of thunderstorms come through. That didn't produce a lot of wind, but it had those bad thunderstorms. Those were two very, very different kinds of events. Working with the weather team, we can better understand the impact of those. In the end, we want to classify what kind of event it is and translate that to a number of outages. And so the weather team's a critical partner. Yeah, just the two bad storms that we've had in the last week, completely different kinds of storms. And the question was, did we tailor the model? Yes, because we have different predictors. We've got one predictor that takes wind into account. Another one would take probability of thunderstorms into account. Last week, wind was high, thunderstorms was low. Yesterday, it was the other way around. So it's a factor in the model.
Hi.
Hi.
Thank you very much. So weather modeling is particularly sensitive to initial conditions. And you may have answered this in your wonderful presentation when you do ensembling, but my specific question is, do you, before you ensemble, do you kind of do like a pre-ensembling where you have like a range of values of what kind of wind speeds or what kind of probability of thunderstorms that you do for your various time outages? So I can be even more specific. So.
His question should be another slide in this deck. The short answer is yes.
Okay. I mean, sure, because, yeah, it's highly sensitive to initial conditions, so, sure.
Well, two things about that. Highly sensitive to initial conditions. That's going to be especially true for these sequence models. In those conditions, because it's so highly sensitive to initial conditions, two things. One, LSTM models. It's a specific kind of neural net. What it does, it's got a funny sounding name, long short-term memory. What does that mean? What it means is, do we go back 3 days, because that's when the weather pattern started, or do we go back 4 or 5 or 6 days because that's when the weather pattern started? How much back memory do you have to set up those initial conditions? LSTM, we have found, works really well for weather models because of what this gentleman from Consumers, he knows what we're doing, and because of what he just described, yeah, LSTM models are particularly strong. Point number 2. Regression models have no initial conditions. They are purely instantaneous. They are points in time. At this moment, with this much forecast, wind and thunderstorm probability and dew point and all the rest, here are the outcomes. There's no initial setup. So that question, this has strengths and weaknesses. When you have initial conditions and they're informative, sort of a Bayesian process, that's a real asset. But then it becomes, as the gentleman just said, very sensitive to initial conditions, and that can become a weakness if you get the initial conditions wrong. The flip side of that is regression models that have no initial conditions. It's purely instantaneous, and so that has both strengths and weaknesses to it. Would you agree?
Yeah, thank you.
Early on in your presentation, you mentioned that you use 5 years of historical outage data to feed your model. Is there a reason that you wouldn't want to use more than 5 years?
Climate change. Older data just isn't as reliable for how things are in the world today.
Both outage data and like the weather data that you're pulling from NOAA?
I would say yes. The other thing about, at least for DTE, and you'll see that for a lot of companies, if you're measuring different stuff, you'll find changes in policy for how outages get counted. Now, for us, that puts a total limit of about 8 years. Past a certain date, it's a completely different counting system, and we couldn't go back further even if we wanted to. Well, we could, and then we'd have to scale up to the new system. So we could adjust it with a scale factor. But you can see business decisions. For example, if you're doing financial forecasting, will someone go south on a loan or not? Well, what qualifies? You can have a business policy to do more to help people to make sure they don't default. Now that changes the numbers for who gets defaulted. And so your history gets corrupted. When you're doing these long-term longitudinal studies, this is what I do for a living. When you do longitudinal studies, you have to watch out that the things you're flagging as yeses and nos, the rules can change at points in time. And that sets a limit to how far back you can go. For us, it was more like 8 years, and then they just changed the rules in February of last year, so we can't use the most recent data either. We had to block that out. We used 2018 through 2022 because we changed the rules for counting again in February 23. Have to be aware of what that is. So we took a 5-year period. 5-year period was enough to get the seasonality patterns. We wanted to have 5 seasons. And so it wasn't too dependent on a particularly good year or bad year, like last year was a bad year. 5 years just seems to work out well for us. Are we done? We're done. Thank you very much. I am available for questions. Thank you.